the birth and life of a star. Before we dive into how stars die, we need to understand how they are born and how they live. Stars, those luminous balls of gas that light up the cosmos, have fascinating life cycles that span millions, or even billions of years. Let's start at the beginning of their existence, where they are born from the cold darkness of space. Stars are born in dense regions of gas and dust, known as molecular clouds or stellar nurseries. These clouds, often located in the spiral arms of galaxies, provide the perfect conditions for star formation. Gravity causes clumps of gas to collapse, triggering a chain reaction. As the cloud collapses, the temperature inside rises, and the pressure increases. The core of the collapsing gas eventually gets hot enough, reaching temperatures of millions of degrees Kelvin for nuclear fusion to begin. Fusion, the process that powers stars, occurs when hydrogen atoms smash into each other with enough force to fuse into helium, releasing immense amounts of energy in the form of light and heat. One of the most famous stellar nurseries is the Orion Nebula, located about 1,350 light-years from Earth. This immense cloud of gas and dust is a bustling site of star formation, with dozens of new stars in various stages of development. These nurseries are the cradles of stellar life, where gas giants and sun-like stars begin their long journey. Once nuclear fusion kicks off in a star's core, it enters the most stable part of its life, the main sequence. This phase can last for billions of years, depending on the star's mass. Stars like our Sun spend about 10 billion years in this phase. The star's core remains balanced, with the outward pressure from nuclear fusion counteracting the inward pull of gravity. During this phase, stars continuously convert hydrogen into helium, shining brightly in the process. The Sun, for instance, is currently about halfway through its main sequence phase. It's been shining for about 4.5 billion years and will continue to do so for roughly another 5 billion years. Stars that are more massive than the Sun, however, burn through their hydrogen much faster, sometimes exhausting their fuel in just a few million years. The mass of a star at birth is the key factor in determining its ultimate fate. Low-mass stars, like red dwarfs, are much cooler and dimmer than stars like the Sun. They burn their hydrogen so slowly that they can last for hundreds of billions of years, far longer than the current age of the universe. On the other hand, massive stars, those that are at least 8 times the mass of the Sun, lead much more dramatic lives. They burn their fuel quickly and live fast, dying in spectacular explosions known as supernovae. As stars age, they gradually exhaust the hydrogen in their cores. When this happens, the core contracts under gravity and the outer layers expand, turning the star into a red giant. The Sun, for example, will become a red giant in about 5 billion years. In this phase, the outer layers of the star balloon outwards, potentially engulfing nearby planets. For our Sun, this expansion could mean the end of Mercury and Venus, and possibly Earth itself, depending on how far the Sun's outer layers extend. The color and size of a red giant vary depending on the mass of the original star. While the core of the star contracts, its outer envelope swells to enormous proportions. At this stage, the star is cooler on the surface, which is why it appears red rather than yellow or blue. The red giant phase is short-lived compared to the star's life on the main sequence, typically lasting only a few million years. As fascinating as the life of a star is, its death is just as extraordinary. When the star reaches the end of its life, it will either shrink into a white dwarf or go out in a blaze of glory, depending on its size. But that's a story for the next chapter. The red giant phase, a star's final show. As a star like the Sun approaches the end of its main sequence life, it begins to undergo dramatic changes. The hydrogen fuel in the core becomes exhausted, and the star can no longer support the nuclear fusion that has kept it stable for billions of years. This is when the star begins its transformation into a red giant, a process that drastically alters its size, luminosity, and internal structure. The key event that triggers the red giant phase is the depletion of hydrogen in the star's core. With no more hydrogen to fuse, the balance between radiation pressure and gravity breaks down. Gravity wins, and the core begins to collapse under its own weight. As the core contracts, it heats up. Temperatures can reach up to 100 million degrees Kelvin. This intense heat ignites hydrogen fusion in a shell surrounding the now helium-rich core. This shell burning produces even more energy than when the star was on the main sequence. The outward pressure from this shell burning causes the outer layers of the star to expand dramatically, turning the star into a swollen, bloated red giant. The exact size of a red giant depends on the mass of the star, but it can expand to hundreds of times its original diameter. For perspective, when the Sun becomes a red giant, it could extend as far as the orbit of Earth, which would mean the end of our planet. Earth's oceans will evaporate, and the surface will be scorched by the intense heat from the expanding Sun. In stars like the Sun, the core continues to collapse until it reaches temperatures high enough to ignite helium fusion, a process known as the helium flash. This fusion process turns helium into carbon and oxygen in the core, releasing a tremendous amount of energy. However, helium fusion is less efficient than hydrogen fusion, so this phase doesn't last nearly as long. The helium flash is a brief but intense event that signals the beginning of the next phase in the life of a star. Once the helium in the core begins to fuse, the star temporarily shrinks, and its outer layers cool slightly. But this period of stability is fleeting compared to the billions of years spent in the main sequence. Two well-known red giants visible to the naked eye are Betelgeuse in the constellation Orion and Aldebaran in Taurus. Betelgeuse, a massive star nearing the end of its life, has been the subject of much speculation and fascination. Astronomers believe Betelgeuse could go supernova at any time in the next 100,000 years, a blink of an eye in cosmic terms. It is a massive red supergiant, much larger and more luminous than the Sun, and its eventual explosion will be a spectacular event visible even from Earth. Aldebaran, on the other hand, is a red giant of more moderate mass. It has already exhausted the hydrogen in its core and is now fusing helium. Aldebaran will eventually shed its outer layers and become a white dwarf, following the quieter path typical of stars that are not massive enough to go supernova. For stars with a mass less than about 8 times that of the Sun, the red giant phase marks the beginning of the end. Once these stars have burned through their helium, they don't have the mass needed to reach the temperatures required for further fusion. Without the energy from nuclear fusion, the core of the star will continue to collapse under the force of gravity. The core, made mostly of carbon and oxygen at this stage, becomes degenerate, meaning that it resists further collapse due to quantum mechanical effects rather than fusion. This core will eventually become a white dwarf, a dense, Earth-sized remnant of the once massive star. Meanwhile, the outer layers of the star are gently ejected into space, forming what's known as a planetary nebula. These glowing clouds of gas are illuminated by the remaining heat of the central white dwarf and create some of the most beautiful structures in the universe. Famous examples of planetary nebulae include the Ring Nebula in the constellation Lyra and the Helix Nebula in Aquarius. The red giant phase may last for a few million years, but it's only a brief chapter in the life of a star. As the outer layers of the star drift away to form a planetary nebula, the remaining core cools and shrinks into a white dwarf. For stars like the Sun, this is the final stage of their lives. The white dwarf will gradually radiate away its remaining heat over billions of years, slowly fading into a cold, dark remnant known as a black dwarf, though the universe isn't old enough for any black dwarfs to exist just yet. In the next chapter, we'll explore the spectacular deaths of more massive stars, those that end their lives in violent explosions known as supernovae, leaving behind neutron stars or black holes. Supernovae, the explosive deaths of massive stars. While low and medium mass stars like the Sun end their lives quietly, the death of a massive star is a completely different story. Stars that are at least 8 times more massive than the Sun meet a spectacular and violent end: the supernova. These are among the most energetic events in the universe, capable of outshining entire galaxies for a brief period and dispersing heavy elements like iron, gold, and uranium into the cosmos, elements that eventually form planets, life, and even us. Massive stars, unlike their smaller counterparts, live fast and die young. A star with 20 times the mass of the Sun might live only a few million years, an instant in cosmic time. These stars go through similar stages as smaller stars, burning hydrogen in their cores to create helium. But because of their larger mass, they burn through their fuel much faster. As a massive star ages, it moves through different stages of fusion. After exhausting the hydrogen in its core, it begins fusing helium into carbon, then carbon into heavier elements like neon, oxygen, and silicon. Each stage of fusion releases energy that prevents the star from collapsing under its own gravity, but the clock is ticking. The star's energy output becomes increasingly erratic, and it swells into a red supergiant, much larger and more luminous than a typical red giant. One of the most famous red supergiants is Betelgeuse, which is located in the constellation Orion. Betelgeuse is already nearing the end of its life, and it's expected to go supernova within the next 100,000 years, a blink of an eye in cosmic terms. When it does, the explosion will be visible from Earth, even during the day. The key moment in a massive star's life is the production of iron in its core. Fusion reactions that produce lighter elements release energy, but fusing iron consumes energy rather than releasing it. Once the core of a massive star fills with iron, the star is doomed. Without the energy from fusion to support the core against gravity, the core collapses in on itself within seconds. As the core collapses, it reaches incredible densities, and the temperature skyrockets to billions of degrees Kelvin. The outer layers of the star, which are still burning lighter elements, suddenly collapse inward as well, smashing into the dense core and rebounding outward in a tremendous explosion. This is the supernova, and it can release as much energy in a few seconds as the Sun will in its entire lifetime. There are two main types of supernovae: core collapse supernovae, which occur when massive stars exhaust their nuclear fuel, and type Ia supernovae, which involve white dwarfs in binary systems. Core collapse supernovae. These are the supernovae we've been discussing. When a massive star's core collapses, the rebound causes a powerful explosion that can briefly outshine an entire galaxy. This type of supernova leaves behind either a neutron star or a black hole, depending on the mass of the original star. Type Ia supernovae. These occur in binary systems where a white dwarf is paired with another star. Over time, the white dwarf steals material from its companion until it reaches a critical mass. At this point, runaway nuclear reactions occur, causing the white dwarf to explode. Unlike core collapse supernovae, type Ia supernovae leave nothing behind but a cloud of expanding debris. These explosions are incredibly useful for astronomers because they all occur at a similar mass, making them reliable, standard candles for measuring distances in the universe. A supernova explosion has far-reaching consequences. First, it enriches the surrounding space with heavy elements. Everything heavier than iron, like gold, silver, and uranium, is produced in supernovae. These elements are essential for forming rocky planets and life itself. In fact, the iron in your blood and the calcium in your bones were forged in the hearts of ancient stars and spread through space by supernovae billions of years ago. The shockwave from a supernova can also trigger the formation of new stars. When the explosion slams into nearby clouds of gas and dust, it compresses them, creating the conditions for new stars to form. In this way, supernovae play a vital role in the ongoing cycle of star birth and death that has shaped our galaxy for billions of years. One famous example of a supernova remnant is the Crab Nebula, located about 6,500 light-years from Earth in the constellation Taurus. This nebula was formed by a supernova explosion observed by Chinese astronomers in the year 1054. At the center of the nebula lies a neutron star, the incredibly dense remnant of the original star's core. In some cases, the core of a massive star doesn't completely collapse into a black hole. Instead, it becomes a neutron star, a dense ball of neutrons left over from the core collapse. Neutron stars are incredibly compact. They can have a mass greater than the Sun, but are only about 12 miles in diameter. A teaspoon of neutron star material would weigh as much as a mountain on Earth. Neutron stars often rotate rapidly, and their magnetic fields can accelerate charged particles to near the speed of light. As these particles spiral around the magnetic field lines, they emit beams of electromagnetic radiation, creating what's known as a pulsar. Pulsars are like cosmic lighthouses, emitting regular pulses of radiation that we can detect from Earth. For the most massive stars, even neutron degeneracy pressure isn't enough to halt the collapse of the core. In these cases, the core continues to collapse until it forms a black hole, a region of space where gravity is so strong that not even light can escape. Black holes are among the most mysterious objects in the universe, and their formation marks the ultimate death of a star. In the next chapter, we'll explore the quieter fate of stars that don't go supernova. the creation of white dwarfs and planetary nebulae, the final stage for stars like our Sun. White dwarfs, the silent death of a star. Not all stars die in a blaze of glory. While massive stars end their lives in spectacular supernovae, smaller stars, like our Sun, have a much quieter yet equally fascinating death. After the red giant phase, these stars slowly cool and shrink, leaving behind dense remnants known as white dwarfs. Though less dramatic than a supernova, the formation of a white dwarf marks the final stage in the life cycle of most stars in the universe. To understand how white dwarfs are formed, we need to revisit the red giant phase. As we discussed earlier, when a medium-sized star, with a mass up to about 8 times that of the Sun, exhausts its nuclear fuel, it expands into a red giant. During this phase, the star fuses helium into heavier elements like carbon and oxygen. However, once the star runs out of helium, it can no longer sustain the fusion reactions necessary to counteract the force of gravity. As the core contracts, the outer layers of the star are blown away in a series of gentle but spectacular pulses. These ejected outer layers form what's known as a planetary nebula, a glowing shell of gas illuminated by the remaining heat of the core. Famous examples of planetary nebulae include the Ring Nebula in the constellation Lyra and the Cat's Eye Nebula in Draco. At the heart of the planetary nebula, the core of the star continues to shrink and cool. Without nuclear fusion to provide outward pressure, the core is held up by a different force, electron degeneracy pressure. This pressure arises from the quantum mechanical properties of electrons, which prevent them from being compressed into the same space. The core that remains is incredibly dense, typically around the size of Earth, but with a mass comparable to the Sun. This remnant core is what we call a white dwarf. White dwarfs are remarkable objects, and their properties are both surprising and extreme. Despite their relatively small size, comparable to Earth, white dwarfs are incredibly dense. A single cubic centimeter of white dwarf material can weigh over a ton. This density is due to the fact that the matter in a white dwarf is packed as tightly as the laws of quantum mechanics allow. The force that prevents further collapse, electron degeneracy pressure, is a consequence of the Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state simultaneously. White dwarfs are also extremely hot when they first form, with surface temperatures reaching up to 100,000 degrees Kelvin. However, since no nuclear fusion is occurring in the core, they gradually cool over billions of years. As they cool, they lose their luminosity and fade into the darkness. It's estimated that after about 10 billion years, a white dwarf will become so dim that it's nearly invisible. These fully cooled white dwarfs, known as black dwarfs, are theoretical, as the universe is not yet old enough for any to have formed. One of the most important aspects of white dwarfs is their mass limit, known as the Chandrasekhar limit. Named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, this limit defines the maximum mass a white dwarf can have before it collapses into a neutron star or black hole. The Chandrasekhar limit is about 1.4 times the mass of the Sun. If a white dwarf exceeds this limit, usually by accreting mass from a companion star in a binary system, it will no longer be able to support itself against gravitational collapse. When this happens, the white dwarf can undergo a catastrophic explosion known as a Type Ia supernova, which completely destroys the star. Unlike the core collapse supernovae of massive stars, a Type Ia supernova leaves nothing behind, only an expanding cloud of gas and debris. There are several well-known examples of white dwarfs in the night sky, and 2 of the most famous are Sirius B and Procyon B. Sirius B is the companion to Sirius A, the brightest star in the night sky. Though invisible to the naked eye, Sirius B is one of the most studied white dwarfs. It was first discovered in 1862 by American astronomer Alvan Graham Clark. Sirius B has a mass nearly equal to that of the Sun, but its diameter is only about 12,000 kilometers, roughly the size of Earth. Its surface temperature is still around 25,000 degrees Kelvin, though it is slowly cooling over time. Procyon B is the faint companion to Procyon A, one of the brightest stars in the constellation Canis Minor. Like Sirius B, Procyon B is a white dwarf, but it is slightly less massive than Sirius B. Procyon B has been a subject of study since the early 20th century, and its discovery helped astronomers better understand the properties and evolution of white dwarfs. While solitary white dwarfs like Sirius B and Procyon B are fascinating in their own right, white dwarfs in binary star systems can lead to even more dramatic events. In a close binary system, a white dwarf can siphon material from its companion star. This process of mass transfer can have several outcomes, depending on the mass of the white dwarf and the amount of material it accretes. If a white dwarf accumulates enough material from its companion star, it can ignite runaway nuclear fusion on its surface, producing a nova. Unlike a nova doesn't destroy the white dwarf. Instead, it produces a sudden and dramatic increase in brightness as the outer layers of the white dwarf are blown off. These events can repeat over time as the white dwarf continues to siphon material from its companion. In some cases, the white dwarf can accrete enough material to push its mass over the Chandrasekhar limit. When this happens, the white dwarf can no longer support itself, and it undergoes a thermonuclear explosion, a type Ia supernova. This type of supernova is incredibly useful for astronomers because it occurs at a consistent mass, making it a reliable standard candle for measuring cosmic distances. As we've mentioned, the Sun will eventually become a white dwarf. In about 5 billion years, after it has passed through the red giant phase, the Sun will shed its outer layers and leave behind a white dwarf roughly the size of Earth. This white dwarf will slowly cool over the following billions of years, eventually fading into a black dwarf. By that time, the planets of the solar system will likely be long gone. Mercury and Venus will be swallowed by the expanding Sun during its red giant phase, and Earth's fate remains uncertain. If Earth survives, it will be a cold, barren rock orbiting a dim, cooling white dwarf. In the next chapter, we'll explore the mysterious world of neutron stars and pulsars, ultra-dense remnants of massive stars that provide some of the most extreme environments in the universe. Neutron stars and pulsars, the cosmic lighthouses. As we journey through the final stages of stellar evolution, we now enter the world of neutron stars, arguably some of the most fascinating and extreme objects in the universe. When a massive star undergoes a supernova, its core may collapse into a neutron star, a dense remnant formed almost entirely of neutrons. These stars are compact, incredibly dense, and often rotate at incredible speeds. In some cases, neutron stars emit beams of radiation, becoming what we call pulsars, nature's cosmic lighthouses. When a star with a mass between 8 and 20 times that of the Sun runs out of nuclear fuel, its core collapses in on itself during the final stages of a supernova. The intense gravitational forces are so strong that protons and electrons in the core combine to form neutrons. This process of neutronization results in the formation of a neutron star, an object with a radius of only about 12 to 15 miles, but a mass greater than the Sun. To put this into perspective, imagine compressing the entire mass of the Sun into an object the size of a city. The density of a neutron star is beyond comprehension. A single teaspoon of neutron star material would weigh about 6 billion tons. This incredible density is supported by neutron degeneracy pressure, which, much like electron degeneracy pressure in white dwarfs, prevents the star from collapsing further. Neutron stars have several properties that make them some of the most bizarre objects in the universe. They are incredibly dense, hot, and often rotate rapidly. These characteristics are a direct result of the physics governing their formation. As mentioned, neutron stars are incomprehensibly dense. They pack a mass greater than that of the Sun into a space only about 12 miles across. The surface gravity on a neutron star is about 200 billion times stronger than gravity on Earth. If you dropped an object from just 1 meter above a neutron star's surface, it would hit the ground in a microsecond, traveling at about 2,000 kilometers per second. Newly formed neutron stars can have surface temperatures exceeding 1 million degrees Kelvin. Over time, they cool, but the process is slow because of the intense density. Even after millions of years, neutron stars remain incredibly hot compared to other stellar remnants. When a massive star's core collapses, the conservation of angular momentum causes the neutron star to spin rapidly. Some neutron stars can rotate hundreds of times per second. These incredibly fast-spinning neutron stars are called millisecond pulsars. Over time, the rotation of a neutron star slows down due to energy loss, but this process can take millions of years. In 1967, a groundbreaking discovery was made by Jocelyn Bell Burnell, a graduate student at Cambridge University. While studying radio waves from distant objects in space, Bell Burnell observed regular, repeating signals, pulses that occurred at precise intervals. Initially, the source of these signals was unknown, and the signals were even jokingly dubbed "little green men," as some speculated that they could be of alien origin. However, it soon became clear that these pulses were being emitted by neutron stars. These rapidly rotating neutron stars, now known as pulsars, emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like the light from a lighthouse. When one of these beams crosses Earth, we observe it as a pulse of radiation. Pulsars are fascinating for both their regularity and their speed. Some pulsars rotate hundreds of times per second, making them the most precise cosmic clocks known to humanity. In fact, certain pulsars are so stable that they can be used to test fundamental theories of physics, such as general relativity. A pulsar's behavior is governed by its extreme magnetic field and rapid rotation. Neutron stars typically have magnetic fields trillions of times stronger than Earth's. This immense magnetic field accelerates charged particles in the star's vicinity, producing radiation in the form of radio waves, X-rays, or even gamma rays. The radiation is emitted from the magnetic poles of the star, and because the rotation axis of the neutron star is not aligned with its magnetic poles, the radiation beams sweep through space. The rotation of the neutron star causes the beams to sweep across the sky, and if Earth happens to be in the path of one of these beams, we observe a pulse. These pulses can occur with astonishing regularity, often hundreds of times per second. The regularity of pulsar emissions allows astronomers to use pulsars as natural clocks, and in some cases, pulsars are even more accurate than atomic clocks on Earth. One of the most famous pulsars is the Crab pulsar, located at the center of the Crab Nebula, a remnant of a supernova that was observed by Chinese astronomers in the year 1054. The Crab pulsar spins about 30 times per second and emits pulses of radiation across multiple wavelengths, including radio waves, visible light, X-rays, and gamma rays. The discovery of the Crab pulsar in the 1960s provided strong evidence that pulsars were indeed rotating neutron stars. Its rapid rotation and powerful emissions are a direct result of the supernova explosion that gave birth to the Crab Nebula. Some pulsars exist in binary systems, where the neutron star orbits a companion object. These systems provide valuable laboratories for testing the laws of physics, especially Einstein's theory of general relativity. One of the most famous examples is the binary pulsar PSR-B 1913+16, discovered by Russell Hulse and Joseph Taylor in 1974. This pulsar is in orbit with another neutron star, and as the two objects orbit each other, they lose energy by emitting gravitational waves. These ripples in space-time, predicted by Einstein, cause the orbit of the binary system to shrink over time. Hulse and Taylor's precise measurements of the system confirmed the existence of gravitational waves, and they were awarded the Nobel Prize in Physics in 1993 for their discovery. More recently, gravitational waves have been directly detected by the LIGO and Virgo observatories, providing even more evidence for the existence of these elusive ripples in space-time. Neutron stars are incredibly long-lived compared to other stellar remnants. However, over billions of years, they slowly lose their rotational energy and cool down. Eventually, they become undetectable as pulsars. Some neutron stars may be drawn into collisions with other objects, such as other neutron stars or black holes. These cataclysmic events can produce bursts of gamma rays and powerful gravitational waves. In some cases, the merger of two neutron stars may lead to the formation of a black hole, while in others, it may result in the production of heavy elements like gold and platinum. These neutron star collisions have been observed through both electromagnetic radiation and gravitational waves, providing valuable insights into the behavior of matter under extreme conditions. In the next chapter, we will dive into the most enigmatic of all stellar remnants, black holes. These regions of space, where gravity is so strong that nothing, not even light, can escape, represent the ultimate end of massive stars. Black holes, the ultimate fate of massive stars. We've explored the lives of stars, their peaceful deaths as white dwarfs, and their explosive ends as supernovae, leaving behind neutron stars and pulsars. Now, we turn to the most mysterious and powerful remnants of all, black holes. These enigmatic objects are born when the most massive stars collapse under their own gravity, creating a region of space where nothing, not even light, can escape. Black holes are not only the ultimate end for some stars, but also some of the most extreme environments in the universe. Black holes form from the remnants of very massive stars, typically those with more than 20 times the mass of the Sun. When such a star reaches the end of its life, it undergoes a core collapse supernova. During this event, the star's core collapses under the intense force of gravity, and if the remaining core has enough mass, greater than about 3 times the mass of the Sun, gravity overwhelms all other forces, and the core continues to collapse, forming a black hole. This collapse creates a singularity, a point of infinite density, where the laws of physics as we understand them break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape. Once something crosses the event horizon, it's lost forever to the black hole, trapped by its immense gravitational pull. The size of the event horizon, known as the Schwarzschild radius, depends on the mass of the black hole. For example, a black hole with the mass of the Sun would have a Schwarzschild radius of just about 3 kilometers, while a black hole 10 times more massive would have a radius of 30 kilometers. Despite their relatively small size, black holes can have an enormous influence on their surroundings. The black holes that form from the collapse of massive stars are known as stellar mass black holes. These objects typically range from about 3 to 20 times the mass of the Sun, though some can be even more massive if they merge with other black holes or accrete matter from their surroundings. Stellar mass black holes can often be found in binary systems, where they interact with a companion star. In these systems, the black hole can pull material from the companion star, forming an accretion disk, a swirling ring of gas and dust that spirals toward the event horizon. As the material in the accretion disk accelerates and heats up, it emits X-rays, which can be detected by telescopes on Earth. This is how many black holes are discovered, as the X-ray emissions from the accretion disk are far more detectable than the black hole itself. One of the most famous stellar mass black holes is Cygnus X1, located about 6,000 light-years from Earth in the constellation Cygnus. Cygnus X1 was one of the first black holes to be discovered and remains one of the best-studied black holes in the universe. It has a mass about 14 times that of the Sun and is part of a binary system with a blue supergiant star. The intense X-rays emitted from Cygnus X1's accretion disk were the first clues that led astronomers to identify it as a black hole. While stellar mass black holes are the remnants of individual stars, there is another class of black holes that are far more massive, supermassive black holes. These giants, with masses ranging from millions to billions of times that of the Sun, are thought to reside at the centers of most galaxies, including our own Milky Way. The origin of supermassive black holes is still a mystery. Some theories suggest they formed from the collapse of massive gas clouds in the early universe, while others propose that they grew from smaller black holes that merged and accreted matter over billions of years. Regardless of how they form, supermassive black holes are crucial to the formation and evolution of galaxies. The supermassive black hole at the center of the Milky Way is called Sagittarius A. It has a mass of about 4 million times that of the Sun and is located about 26,000 light-years from Earth. While Sagittarius A is relatively quiet, supermassive black holes in other galaxies can be far more active, pulling in vast amounts of material and emitting powerful jets of radiation that can be seen across the universe. These active black holes are known as quasars, and they are some of the brightest objects in the cosmos. The defining feature of a black hole is its event horizon, the point of no return. Once anything, matter, light, or information, crosses this boundary, it is lost forever. The event horizon is not a physical surface, but rather a boundary in space beyond which the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can escape the black hole's gravity. What lies beyond the event horizon is a mystery. At the center of the black hole is the singularity, where the curvature of space-time becomes infinite and the known laws of physics break down. General relativity, which describes gravity and the behavior of space-time, predicts the existence of singularities, but quantum mechanics, which governs the behavior of particles on very small scales, cannot yet fully describe what happens at these extreme points. This conflict between general relativity and quantum mechanics has led physicists to seek a unified theory of quantum gravity, which could explain the behavior of black holes at the smallest scales. One promising candidate is string theory, which proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. However, a complete theory of quantum gravity remains elusive. In the 1970s, physicist Stephen Hawking made a groundbreaking prediction about black holes. They are not entirely black. According to Hawking radiation, black holes can emit particles due to quantum effects near the event horizon. This radiation causes the black hole to lose mass over time, eventually leading to its evaporation. Hawking radiation occurs because, according to quantum mechanics, pairs of virtual particles are constantly being created and annihilated in empty space. Near the event horizon of a black hole, one of these virtual particles may fall into the black hole while the other escapes. To an outside observer, it appears as though the black hole is radiating particles. Over incredibly long timescales, this process causes the black hole to lose mass. And if it continues long enough, the black hole could eventually evaporate completely. For stellar mass and supermassive black holes, the timescale for evaporation is far longer than the current age of the universe, so we are unlikely to witness this process anytime soon. However, for smaller, hypothetical primordial black holes, which may have formed in the early universe, Hawking radiation could be a significant factor in their evolution. One of the most intriguing effects of black holes is the phenomenon of time dilation. According to Einstein's theory of general relativity, time passes more slowly in strong gravitational fields. Near the event horizon of a black hole, the gravitational field is so intense that time can appear to nearly stop for an outside observer. If you were to watch an object falling toward a black hole, you would see it slow down as it approached the event horizon. To you, it would never appear to cross the event horizon, as time near the black hole stretches out to infinity. However, from the perspective of the object itself, time would continue as normal, and it would fall into the black hole without noticing any dramatic change. This effect, known as gravitational time dilation, has been confirmed by experiments on Earth and in space, though the extreme conditions near black holes make the effect far more pronounced. It's one of the many ways in which black holes challenge our understanding of the nature of time and space. Black holes are more than just cosmic oddities. They play an essential role in shaping galaxies and the universe. Supermassive black holes at the centers of galaxies can regulate star formation through their powerful jets and winds, influencing the evolution of entire galaxies. Stellar mass black holes in binary systems can produce bursts of X-rays and gamma rays, offering clues about the behavior of matter under extreme conditions. Moreover, black holes are crucial for testing the laws of physics. By observing the behavior of matter and light near black holes, astronomers can test predictions made by general relativity and quantum mechanics. The study of black holes has already led to groundbreaking discoveries, such as the detection of gravitational waves from black hole mergers by the LIGO and Virgo observatories. In the next chapter, we will explore the final mysteries of stellar evolution, including the theoretical existence of black dwarfs and the ultimate fate of stars and black holes in the distant future of the universe. The final fate of stars, black dwarfs, and the end of stellar evolution. As we approach the conclusion of our journey through the life and death of stars, we now turn to the farthest future of the cosmos, when the last embers of stellar light fade away. While we have explored the explosive deaths of massive stars and the quiet ends of smaller ones, there is a final, lesser-known chapter in stellar evolution: the formation of black dwarfs. Black dwarfs represent the ultimate fate of stars, like our Sun, as they cool and darken over unimaginable stretches of time, becoming cold, inert remnants. In this chapter, we will explore the fate of white dwarfs as they slowly fade into black dwarfs, the theoretical nature of these objects, and the distant future of the universe itself, when all stars have burned out and the universe enters its final stages. We've already seen how stars like the Sun end their lives by becoming white dwarfs, dense stellar remnants supported by electron degeneracy pressure. White dwarfs do not undergo nuclear fusion. so they do not produce new energy. Instead, they radiate away the heat left over from their formation. This process of cooling takes an extraordinary amount of time. Initially, white dwarfs are extremely hot, with surface temperatures reaching up to 100,000 degrees Kelvin. Over billions of years, they cool to much lower temperatures, gradually fading in luminosity. However, due to their small size and high density, the cooling process is very slow. Even after tens of billions of years, white dwarfs will still be warm and dimly visible. The key to understanding the future of white dwarfs lies in the concept of entropy. As white dwarfs cool, they lose entropy, gradually approaching a state of maximum disorder. When they have radiated all of their thermal energy, they will become cold, dark objects. These are black dwarfs, hypothetical remnants that have cooled so much that they no longer emit significant heat or light. Black dwarfs are theoretical objects, as the universe is not yet old enough for any to have formed. The oldest known white dwarfs are about 12 billion years old, and they still radiate detectable heat. To fully cool into black dwarfs, white dwarfs would need trillions of years, much longer than the current age of the universe. As a white dwarf cools, its internal temperature drops and the atoms within it slow their movements. Eventually, the white dwarf will reach thermal equilibrium with the cosmic microwave background, the faint, residual radiation left over from the Big Bang. Once this happens, the white dwarf will no longer radiate any energy into space and will effectively become a black dwarf. Black dwarfs are thought to be composed mostly of carbon and oxygen, the elements left behind from the earlier stages of stellar evolution. These elements would be packed into a dense, crystal-like structure, similar to a giant diamond in space. The black dwarf would be inert, with no internal energy sources, slowly drifting through the dark universe. The eventual formation of black dwarfs marks the end of stellar evolution for most stars. As the universe ages, fewer and fewer stars will be born. The gas needed to form new stars will be consumed by existing stars, and as time goes on, the remaining stars will burn through their fuel and die. The most numerous stars in the universe are red dwarfs, which are smaller and cooler than stars like the Sun. These stars burn their hydrogen very slowly and can live for trillions of years. Red dwarfs will be the last stars to die, but when they do, they will also end up as white dwarfs, eventually cooling into black dwarfs. Brown dwarfs are objects that are too small to sustain hydrogen fusion in their cores. These failed stars never ignite like true stars and instead cool and fade over time. Brown dwarfs will gradually cool into black dwarfs, though this process will take an even longer time than for white dwarfs. Massive stars that end in supernovae will leave behind neutron stars or black holes. Neutron stars will also cool over time, though the process will take far longer than for white dwarfs. Black holes, on the other hand, will not cool in the same way. However, as we discussed in the previous chapter, black holes may eventually evaporate due to Hawking radiation over extremely long timescales. As the universe expands and cools, the formation of new stars will slow and eventually stop. This process is known as the degenerate era, a time when the universe will be populated primarily by remnants of dead stars, white dwarfs, neutron stars, black dwarfs, and black holes. The degenerate era will last for trillions of years. During this time, existing stars will continue to burn their fuel, but no new stars will form. The gas clouds that once birthed new generations of stars will have been consumed or dispersed. The galaxies themselves will grow dimmer and less active as their stellar populations age and die. Black dwarfs represent the final stage in the life cycle of normal stars. But what happens when all stars have faded into black dwarfs, neutron stars, or black holes? This leads us to one of the most profound questions in astrophysics: the ultimate fate of the universe itself. The current understanding of cosmology suggests that the universe will continue to expand indefinitely. As space expands, the galaxies will drift farther and farther apart, and the universe will grow colder and more isolated. This future scenario is often referred to as the heat death of the universe. In the heat death scenario, the universe reaches a state of maximum entropy, where all energy is evenly distributed and no useful work can be done. In this state, black dwarfs, neutron stars, and black holes will be the last remaining objects in the universe. Over time, even these objects will decay. Neutron stars may collapse into black holes, and black holes themselves may eventually evaporate due to Hawking radiation. In the farthest future, trillions upon trillions of years from now, the universe will become a cold, dark, and lifeless place, with no sources of energy left to power any activity. This is the final fate of all stars and galaxies, a universe that has effectively gone dark. Although this scenario sounds bleak, it is important to remember that these processes take place over incredibly long timescales, trillions, even quadrillions of years. The stars we see today will continue to shine for billions of years before their light finally fades. Red dwarfs, the most numerous stars in the universe, will continue to burn their fuel for trillions of years before they too end up as white dwarfs, and later, black dwarfs. For now, the universe remains filled with light, heat, and activity, but the distant future promises a slow journey toward darkness as the stars gradually wink out. In the next chapter, we'll explore what might lie beyond the heat death of the universe. Are there other possible fates for the cosmos? Could new stars ever be born again? And what will happen to black holes and the remaining matter as the universe continues to expand? Beyond the heat death, the far future of the universe. As we venture deeper into the distant future of the universe, we are faced with some of the most profound and speculative questions in cosmology. In the previous chapter, we explored the concept of the heat death, a scenario in which all stars eventually fade and the universe reaches a state of maximum entropy. However, the story of the cosmos might not end with the heat death. Could there be other possibilities for the future of the universe? Might new processes arise to reshape the cosmos, or is eternal darkness the final chapter? In this chapter, we'll explore what might happen after the stars have all gone dark, examine the role of black holes in the far future, and consider theoretical ideas about the ultimate fate of the cosmos. While much of this discussion ventures into the realm of speculation, it is grounded in modern physics and cosmology. Even after all the stars have burned out, the universe will still contain vast numbers of black holes. These objects, formed from the remnants of massive stars, or from the merging of smaller black holes, will continue to exist for an extraordinarily long time. In fact, black holes may dominate the universe for many trillions of years after the last stars have faded into black dwarfs. However, black holes are not entirely eternal. As we discussed in earlier chapters, Stephen Hawking's theory of Hawking radiation suggests that black holes slowly lose mass over time by emitting tiny amounts of radiation. This process is incredibly slow for large black holes, but over unimaginable timescales, it will lead to the gradual evaporation of black holes. The larger the black hole, the longer it will take to evaporate. For a supermassive black hole like the one at the center of our galaxy, the evaporation process could take over 100 Google, a number written as 1 followed by 100 zeros, years. Stellar mass black holes, which are much smaller, will evaporate more quickly, but still over timescales far exceeding the current age of the universe. As black holes lose mass through Hawking radiation, they will eventually shrink to nothing, disappearing entirely from the cosmos. This marks the end of the black hole era, which could occur far in the future, long after all other cosmic processes have ceased. Even after black holes have evaporated and the universe has reached a state of maximum entropy, some physicists speculate that quantum processes could still occur. According to the laws of quantum mechanics, even in a vacuum, where no particles exist, there are tiny fluctuations of energy. These fluctuations are known as quantum fluctuations, and they play a crucial role in many areas of physics. One possibility is that, over extremely long timescales, quantum fluctuations could trigger the birth of new particles, or even new universes. In a process known as false vacuum decay, a small region of space could undergo a phase transition, creating a new universe with different physical properties. This idea is rooted in the theory of inflation, which suggests that our universe began as a tiny, rapidly expanding region of space following the Big Bang. In the distant future, such quantum processes might allow for the creation of entirely new universes, each with its own set of physical laws and constants. These baby universes could emerge from the decayed remnants of our current universe, leading to an endless cycle of cosmic rebirth. While this idea remains speculative, it offers a tantalizing possibility that the death of our universe may not be the final chapter in the story of the cosmos. Could stars ever be reborn after the heat death of the universe? While it seems unlikely in the traditional sense, there are some theoretical scenarios in which new stars could form in the far future. One such idea involves dark matter, the mysterious substance that makes up about 85% of the mass in the universe. Although dark matter does not interact with light or normal matter in the same way as ordinary particles, some physicists have proposed that dark matter could play a role in future cosmic processes. If dark matter particles were to decay or interact in unexpected ways, they might release energy that could fuel the formation of new structures, possibly even stars. Another speculative idea is the possibility of proton decay. Protons, the building blocks of atomic nuclei, are generally thought to be stable, but some theories of particle physics suggest that they could eventually decay over vast timescales. If protons do decay, this process could release energy and matter in ways that might allow for new stars to form, albeit in a radically different universe from the one we know today. One of the biggest mysteries in cosmology is the nature of dark energy, the force responsible for the accelerated expansion of the universe. Discovered in the late 1990s, dark energy appears to make up about 70% of the total energy content of the universe, yet its true nature remains elusive. The expansion of the universe is currently accelerating due to dark energy, but what will happen to this acceleration in the distant future? There are several possibilities. If dark energy continues to behave as it does now, the universe will keep expanding forever. Galaxies will drift farther and farther apart, eventually becoming so distant that they are no longer visible to each other. Over trillions of years, the universe will grow cold and dark as stars burn out, and black holes evaporate. This is the traditional heat death scenario, where the universe reaches a state of maximum entropy. In a more extreme scenario, dark energy could grow stronger over time, causing the expansion of the universe to accelerate to catastrophic levels. In this Big Rip scenario, the fabric of space-time itself would be torn apart. Galaxies, stars, planets, and even atomic particles would be ripped to shreds as the expansion rate increases to infinity. This cataclysmic event would mark the ultimate destruction of the universe. Another possibility is that dark energy might reverse its effects at some point in the future. If the expansion of the universe slows down and eventually reverses, the universe could begin to contract. Over time, all matter and energy would be drawn back together into a single point, resulting in a big crunch, essentially the opposite of the Big Bang. Some cosmologists speculate that this cycle of expansion and contraction could repeat endlessly, with new universes being born from the collapse of the old. In some versions of the Big Crunch scenario, the universe might experience a big bounce, in which the contraction of the universe leads to a new Big Bang and the birth of a new universe. This cyclical model suggests that the universe could go through infinite cycles of expansion and contraction, with each new universe having its own unique properties. As we've seen, black dwarfs represent the final remnants of stars. Over unimaginable stretches of time, even these inert objects will begin to decay. Theoretical models suggest that, due to processes like proton decay, the very matter that makes up black dwarfs will eventually break down. If protons decay, black dwarfs will slowly disintegrate, leaving behind only a sea of subatomic particles and radiation. In the distant future, after all matter has decayed, the universe will be composed primarily of low-energy radiation, neutrinos, and possibly dark matter. This will be the final stage of the universe's evolution, a cold, dark expanse where no complex structures remain. Could life survive in the far future? Given the extreme conditions of the far future, the survival of life as we know it seems impossible. However, some speculative theories suggest that advanced civilizations might be able to survive or even thrive in the distant future by harnessing exotic energy sources. For example, a sufficiently advanced civilization might be able to extract energy from black holes through processes like Penrose extraction, which involves capturing the rotational energy of a black hole. Alternatively, civilizations might learn to manipulate quantum fluctuations or even create artificial universes in laboratory conditions. While these ideas are purely speculative, they highlight the incredible potential of future technology in ways that transcend our current understanding of physics. The far future of the universe raises some of the deepest and most intriguing questions in all of science. While the heat death and the eventual decay of matter may seem like the final word, the universe is full of surprises. Whether through quantum processes, the formation of new universes, or the manipulation of space-time itself, the future of the cosmos may hold more possibilities than we can currently imagine. In the next chapter, we will explore the most speculative ideas in modern cosmology, including multiverse theories, the potential for other dimensions, and the ultimate fate of consciousness in the universe. The multiverse and other dimensions, the ultimate frontiers of cosmology. As we journey deeper into the mysteries of the universe, we come to one of the most tantalizing and speculative ideas in modern science, the multiverse. The concept of the multiverse suggests that our universe may not be the only one. Instead, it could be one of an infinite number of universes, each with its own laws of physics, constants, and even dimensions. These ideas, while still highly speculative, offer fascinating possibilities for understanding the ultimate fate of the cosmos and the nature of reality itself. In this chapter, we'll dive into the theories of the multiverse, explore the concept of extra dimensions, and consider what these ideas mean for our understanding of space, time, and the future of the universe. The idea of the multiverse arises naturally from several areas of modern physics, including cosmology, quantum mechanics, and string theory. While the multiverse might sound like science fiction, it has roots in serious scientific inquiry, and several different models propose how multiple universes could exist. One of the most widely discussed models of the multiverse comes from cosmic inflation, a theory that explains the rapid expansion of the universe in the moments following the Big Bang. According to inflation theory, our universe underwent a brief but incredibly rapid expansion, causing space to stretch and smooth out. However, this inflationary process might not have stopped everywhere at the same time. Some regions of space may still be inflating, creating new pocket universes with different properties. In this view, our universe is just one bubble in a vast multiverse. Another source of the multiverse concept comes from quantum mechanics, the theory that describes the behavior of particles on the smallest scales. One interpretation of quantum mechanics, known as the many worlds interpretation, suggests that every time a quantum event occurs with multiple possible outcomes, the universe splits into different branches, each representing one of those outcomes. In this scenario, there are countless parallel universes, each with a different version of events. In the realm of theoretical physics, string theory is one of the leading candidates for a theory of everything, a framework that could potentially unify all the forces of nature, including gravity, into a single consistent theory. String theory predicts the existence of extra dimensions beyond the familiar 3 dimensions of space and one of time. Some versions of string theory propose that there are many different ways these extra dimensions can be configured, leading to a vast landscape of possible universes, each with different physical laws. This is known as the landscape multiverse. If the multiverse exists, the possibilities are truly infinite. Each universe in the multiverse could have different physical constants, such as the strength of gravity, the speed of light, or the masses of fundamental particles. In some universes, stars might burn hotter, or gravity might be too weak to allow galaxies to form. In others, the laws of physics could be radically different, creating worlds that are utterly alien compared to our own. The multiverse could also provide an explanation for one of the biggest puzzles in modern cosmology: why the laws of physics in our universe seem so finely tuned for the existence of life. In the anthropic principle, it is suggested that the reason our universe appears so finely tuned is simply because we happen to live in one of the rare universes where the conditions are right for life to evolve. In a multiverse with infinite possibilities, some universes will inevitably have the right conditions for life, while most will not. The idea of extra dimensions is a key feature of string theory and other advanced theories in physics. In our everyday experience, we are familiar with 3 spatial dimensions: length, width, and height, and 1 dimension of time. However, string theory suggests that there could be additional dimensions, hidden from view because they are compactified or curled up at incredibly small scales. In string theory, extra dimensions can be compactified, meaning they are curled up in such a way that they are too small to detect with current technology. These extra dimensions could be just a tiny fraction of a millimeter across, existing in a form that doesn't affect our everyday experience, but plays a crucial role in the fundamental laws of the universe. Another idea related to extra dimensions is brane theory, which is an extension of string theory. In brane theory, our universe is a three-dimensional brane embedded in a higher dimensional space. Other branes, corresponding to other universes, could exist alongside ours in this higher dimensional space, but we would be unaware of them because we are confined to our own brane. This model suggests that the multiverse could be composed of a series of parallel branes, each with its own version of reality. Some versions of string theory propose that extra dimensions could be warped, meaning they influence the fundamental forces of nature in specific ways. For example, gravity might be weaker in our universe because it spreads out across extra dimensions, while the other fundamental forces remain confined to our three-dimensional brane. This could explain why gravity is so much weaker than the other forces, a long-standing mystery in physics. Could we ever access other universes? One of the most exciting and speculative questions about the multiverse is whether it could ever be possible to travel between universes. While this idea currently lies far beyond our technological reach, there are some theoretical possibilities for accessing other dimensions or universes. In Einstein's theory of general relativity, the fabric of space-time can be warped by massive objects. In certain conditions, this warping could create shortcuts through space-time, known as wormholes. Wormholes are hypothetical tunnels that could connect distant parts of our universe or even different universes altogether. While wormholes have not been observed, they are a legitimate solution to Einstein's equations, and some physicists speculate that they could provide a means of accessing other universes in the multiverse. In quantum mechanics, particles can sometimes tunnel through barriers that would be insurmountable according to classical physics. Some theorists have speculated that a similar process might allow for the tunneling of entire universes from one quantum state to another. If this were possible, it might provide a mechanism for traveling between universes, though the details of such a process remain purely speculative. In brane theory, our universe could be one of many branes floating in higher dimensional space. If two branes were to collide, the impact could potentially transfer matter, energy, or information between them, leading to interactions between parallel universes. Some cosmologists have suggested that such brane collisions might even be responsible for the Big Bang that created our universe. The multiverse, if it exists, raises profound questions not just about physics, but about the nature of reality itself. If there are infinite versions of the universe, what does that mean for our understanding of existence? Could there be versions of us living in other universes where different choices have been made and different outcomes have occurred? And what does the multiverse imply about the nature of consciousness and identity? Some philosophers and physicists have speculated that consciousness itself might be a fundamental part of the multiverse. In the many worlds interpretation of quantum mechanics, every decision creates a branching timeline leading to different outcomes in parallel universes. Could consciousness play a role in selecting which branch of the multiverse we experience? Others have speculated that advanced civilizations in the distant future might be able to manipulate the multiverse itself, creating new universes or accessing parallel realities. These ideas stretch the boundaries of both science and philosophy, offering tantalizing possibilities for the ultimate fate of consciousness in the universe. Just as we ponder the future of our universe, we can also speculate about the ultimate fate of the multiverse. If the multiverse is infinite, it may never end. New universes could continue to form forever, with each universe experiencing its own unique evolution. In this view, the multiverse is a never-ending cycle of birth, death, and rebirth, with no ultimate conclusion. Alternatively, the multiverse itself might be governed by higher laws that we do not yet understand. It's possible that even the multiverse could experience a form of heat death, or that new universes could emerge from the decay of old ones. These ideas remain purely speculative, but they offer exciting possibilities for the future of cosmology and our understanding of the ultimate nature of reality. In the next chapter, we'll explore the cutting-edge science of quantum gravity and how it might help us solve some of the deepest mysteries of black holes, the multiverse, and the nature of time. Quantum gravity and the nature of space and time. As we delve into the most profound and fundamental mysteries of the universe, we arrive at one of the biggest unsolved problems in modern physics: the quest for a theory of quantum gravity. This theory, still elusive, seeks to unify the laws of quantum mechanics, which governs the behavior of particles on the smallest scales, with Einstein's theory of general relativity, which describes gravity and the large-scale structure of space and time. The challenge of reconciling these two seemingly incompatible frameworks could hold the key to understanding black holes, the origins of the universe, and even the multiverse. In this chapter, we will explore the cutting-edge science behind quantum gravity, examine the role of space-time in the quantum realm, and consider how this theory could reshape our understanding of the cosmos. At the heart of the search for quantum gravity is the tension between two of the most successful theories in physics: general relativity and quantum mechanics. Albert Einstein's theory of general relativity, developed in the early 20th century, describes gravity as the curvature of space-time. Massive objects like stars and planets bend the fabric of space-time, and this curvature is what we experience as gravity. General relativity has been incredibly successful in explaining large-scale phenomena, such as the orbits of planets, the expansion of the universe, and the behavior of black holes. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales, such as atoms and subatomic particles. It is a highly successful theory that describes phenomena like the behavior of electrons in atoms, the nature of light, and the interactions of fundamental forces. However, quantum mechanics operates in a probabilistic framework where particles can exist in multiple states simultaneously until observed. The problem arises when we try to apply both theories to the same situation, such as the interior of a black hole or the conditions at the very beginning of the universe. General relativity breaks down at the singularity of a black hole, where space-time curvature becomes infinite, while quantum mechanics struggles to describe the gravitational effects on particles at such small scales. This incompatibility suggests that both theories are incomplete, and that a more fundamental theory, quantum gravity, may be needed to describe the universe's most extreme conditions. The search for quantum gravity has led physicists to explore several different approaches, each with its own set of ideas about how to reconcile general relativity with quantum mechanics. While none of these approaches has yet produced a complete theory, they represent exciting progress toward a deeper understanding of the universe. One of the most prominent candidates for a theory of quantum gravity is string theory, which suggests that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings of energy. These strings can have different modes of vibration, which correspond to different particles. String theory also predicts the existence of extra dimensions, beyond the familiar three spatial dimensions and one of time. In some versions of string theory, these extra dimensions are compactified, making them difficult to detect at human scales. String theory offers a potential solution to the problem of quantum gravity by unifying all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, within a single framework. However, string theory has yet to produce definitive predictions that can be tested experimentally, and it remains a highly complex and speculative area of research. Another approach to quantum gravity is loop quantum gravity, which takes a different path from string theory. Loop quantum gravity proposes that space-time itself is quantized, meaning that it is made up of tiny, discrete units rather than being a smooth continuum as described by general relativity. These units are called loops, and they form a kind of quantum fabric of space-time. Loop quantum gravity predicts that space and time are fundamentally granular at the smallest scales, with a minimum length known as the Planck length, approximately 10 to the negative 35th meters. This theory also suggests that the fabric of space-time becomes foamy near black holes and the Big Bang, preventing singularities from forming and potentially resolving the conflict between general relativity and quantum mechanics. A less well-known approach to quantum gravity is causal set theory, which suggests that space-time is not a continuous fabric, but a discrete set of points, like the pixels on a screen. In this view, Space-time is made up of individual events which are connected by a network of cause and effect relationships. This theory attempts to explain how space and time emerge from these fundamental building blocks and how they evolve over time. Another concept closely related to quantum gravity is quantum foam, a term coined by physicist John Wheeler. Quantum foam refers to the idea that space-time at the smallest scales is constantly fluctuating due to quantum effects. These fluctuations create a foamy structure where space-time is constantly being created and destroyed. Quantum foam plays a crucial role in understanding the behavior of black holes and the possible existence of wormholes, shortcuts through space-time that might connect different regions of the universe or even different universes in the multiverse. One of the key motivations for developing a theory of quantum gravity is to resolve the mystery of black holes and the information paradox. According to general relativity, when something falls into a black hole, it is lost forever, trapped beyond the event horizon. However, quantum mechanics suggests that information, such as the properties of particles, cannot be destroyed, even if the particles themselves are consumed by a black hole. This apparent contradiction leads to the black hole information paradox. How can information be preserved if it seems to be lost inside a black hole? Physicists have been grappling with this paradox for decades, and quantum gravity may provide the answer. Some theories suggest that information is stored on the event horizon of the black hole in the form of holography, while others propose that the information is somehow encoded in the Hawking radiation emitted by the black hole. Resolving the information paradox could have profound implications not only for our understanding of black holes, but for the nature of reality itself. If quantum gravity can explain how information is preserved in black holes, it might also shed light on the ultimate fate of the universe and the fundamental structure of space-time. One of the most intriguing ideas to emerge from the study of quantum gravity and black holes is the holographic principle. This principle suggests that all the information contained within a volume of space can be described by information on the surface of that volume, much like a hologram. In other words, the three-dimensional world we experience might be a projection of information encoded on a two-dimensional surface. The holographic principle has its origins in the study of black holes, where it was discovered that the amount of information contained in a black hole is proportional to the surface area of its event horizon rather than its volume. This led to the idea that the entire universe might operate according to a similar principle, where the three-dimensional universe we experience is a kind of projection from a lower dimensional structure. The holographic principle has profound implications for our understanding of the universe. It suggests that space and time might not be fundamental, but rather emergent properties of a deeper, more fundamental reality. In this view, the universe itself could be a kind of hologram, with all the information needed to describe it encoded on a lower dimensional surface. One of the most exciting possibilities of quantum gravity is its potential to explain the origins of the universe. The Big Bang, which marks the beginning of our observable universe, is thought to have been a moment of infinite density and temperature, a singularity where the laws of physics break down. However, if quantum gravity can prevent singularities from forming, it might also provide a more complete picture of what happened at the very beginning. Some versions of quantum gravity suggest that the Big Bang was not the true beginning of the universe, but rather a transition from a previous state. For example, in loop quantum cosmology, an extension of loop quantum gravity, the universe undergoes a bounce where a previous contracting universe rebounds and begins expanding again. This Big Bounce scenario suggests that the universe has gone through cycles of expansion and contraction, potentially for eternity. Other theories propose that the universe emerged from a quantum fluctuation in a pre-existing spacetime, or that it was born from the collision of higher dimensional branes, as suggested by some versions of string theory. These ideas offer exciting possibilities for understanding the ultimate origins of the cosmos and the nature of time itself. While the search for a complete theory of quantum gravity is still ongoing, the progress made so far has already reshaped our understanding of the universe. Whether through string theory, loop quantum gravity, or other approaches, the quest for quantum gravity holds the promise of unlocking the deepest mysteries of the cosmos, from the behavior of black holes to the nature of the multiverse. In the next and final chapter, we will reflect on the implications of these discoveries for our place in the universe and the ultimate fate of space, time, and matter. The ultimate fate of the universe and our place in the cosmos. As we come to the conclusion of our journey through the life cycles of stars, black holes, the mysteries of the multiverse, and the search for quantum gravity, we are left with some of the most profound questions about the ultimate fate of the universe. What lies ahead for the cosmos? What will become of matter, energy, space, and time in the distant future? And perhaps most importantly, what does this all mean for our understanding of our place in the vast, complex universe? In this final chapter, we'll explore the long-term future of the cosmos, reflecting on the implications of the universe's eventual fate for humanity, the nature of existence, and our understanding of the cosmos itself. Is the long-term fate of the universe heat death or something else? The most widely accepted theory for the ultimate fate of the universe is the heat death scenario, where the universe continues to expand forever, growing colder and darker as stars burn out and galaxies drift apart. Over time, all matter will decay, black holes will evaporate, and the universe will approach a state of maximum entropy, where all energy is evenly distributed and no useful work can be done. In this scenario, the universe would eventually reach a state of total darkness, with no sources of heat or light. This idea is rooted in the second law of thermodynamics, which states that entropy, essentially disorder, always increases over time in a closed system. As the universe reaches its thermodynamic equilibrium, it will become a vast, cold, empty expanse. However, while the heat death scenario is the most likely based on current observations, there are other possible outcomes for the universe's future, depending on the nature of dark energy and other unknown factors. If dark energy continues to accelerate the expansion of the universe, it's possible that the expansion rate could increase to catastrophic levels. In the Big Rip scenario, galaxies, stars, planets, and even atoms would be torn apart by the expansion of space-time itself. This would lead to a sudden and violent end for the universe, with everything being ripped apart down to the smallest scales. Another possibility, though less favored by current data, is the Big Crunch, where the expansion of the universe slows down and eventually reverses. In this scenario, gravity would pull all matter back together, leading to a collapse of the universe into a singularity. This collapse could trigger a new Big Bang, leading to a cyclical universe that expands and contracts over and over again. A variation on the Big Crunch is the Big Bounce scenario, where the universe undergoes a series of expansions and contractions. After each contraction, the Big Crunch, the universe bounces back in a new expansion, a Big Bang. In this model, the universe could be infinitely old, with no true beginning or end, but instead a continual cycle of birth, death, and rebirth. Even in the heat-death scenario, quantum fluctuations could continue to occur, creating the potential for new universes to form. These new universes might arise from the decayed remnants of the current universe, in a process known as false vacuum decay. This idea suggests that the death of one universe could lead to the birth of another, creating an endless cycle of cosmic creation. In the far, far future, after trillions of years, the last stars will have burned out and collapsed into white dwarfs, neutron stars, or black holes. White dwarfs will slowly cool and fade into black dwarfs, cold, inert objects that no longer emit heat or light. Neutron stars will also cool, though this process will take even longer due to their incredible density. Eventually, even black dwarfs, neutron stars, and black holes will decay. The hypothetical process of proton decay, predicted by some theories of particle physics, suggests that over incredibly long timescales, far longer than the current age of the universe, protons, the building blocks of atomic nuclei, may decay into lighter particles. This would cause all matter to disintegrate into radiation, leaving behind a universe filled only with low-energy particles and photons. Even black holes, which seem eternal due to their immense gravitational pull, will not last forever. Through Hawking radiation, black holes slowly lose mass over time, eventually evaporating entirely. For the largest black holes, this process could take up to 100 Google years, a Google being one followed by 100 zeros. Once the last black hole has evaporated, the universe will be left with only the faintest traces of radiation and subatomic particles drifting through an ever-expanding void. What does this far-off cosmic future mean for life? Could life, whether biological or technological, survive in such extreme conditions? In the current universe, life as we know it is dependent on the energy produced by stars. As stars burn out and the universe grows colder, the conditions for life will become more and more hostile. If life exists elsewhere in the universe, it will eventually face the same challenges of energy depletion and the slow decline of stellar activity. Some theorists have speculated that advanced civilizations might find ways to survive in the far future by harnessing energy from black holes or tapping into quantum processes. For example, Penrose's process suggests that energy could be extracted from rotating black holes, providing a possible source of power for advanced civilizations. As the universe approaches heat death, the energy required to sustain complex systems, such as life and consciousness, will become increasingly scarce. Eventually, even the most advanced civilizations would face the end of conscious thought as the universe approaches thermodynamic equilibrium. This raises profound questions about the ultimate fate of consciousness and whether it could persist in some form beyond the physical limits of the universe. In light of these grand cosmic timescales, it's natural to reflect on the meaning of our place in the universe. Human civilization has existed for only a tiny fraction of the universe's history, barely a blink of an eye in cosmic terms. And yet, in that brief moment, we have developed the tools and knowledge to explore the universe's deepest mysteries, from the origins of stars to the ultimate fate of space-time. The discovery of black holes, the study of the multiverse, and the search for quantum gravity have revealed just how vast and complex the cosmos truly is. Our universe is filled with awe-inspiring phenomena, from the explosive deaths of stars to the quiet cooling of white dwarfs and the infinite possibilities of other dimensions. And while our understanding of the universe is still incomplete, the quest to answer these profound questions continues to drive scientific discovery and human curiosity. What we learn today about the cosmos will shape the way future generations understand their place in the universe. While the far future of the universe might seem bleak, a cold, dark, lifeless expanse, there is also something deeply inspiring about the scale and majesty of the cosmos. Our universe, born in a fiery Big Bang, has given rise to stars, planets, galaxies, and life itself. It has allowed us to ask the biggest questions. Where did we come from? What is the nature of reality? And what will become of the cosmos in the end? As we continue to explore the universe, we are not just uncovering the secrets of the stars, we are discovering the story of existence itself. Whether the universe ends in a heat death, a big rip, or a new cycle of creation, the journey of understanding our cosmos is an ongoing one, filled with wonder, mystery, and infinite possibilities. In this vast, expanding universe, we are small, yet our ability to explore, to question, and to seek answers makes our place in the cosmos uniquely meaningful. The stars may fade, black holes may evaporate, and the universe may one day go dark. But the human spirit of curiosity and discovery will continue to shine as long as we exist. As we conclude this exploration of the life and death of stars, black holes, and the far future of the universe, we are reminded of the incredible scale and beauty of the cosmos. The stars that light our night sky are not eternal, but their stories of birth, life, and eventual death are part of the grand tapestry of the universe. Understanding their journeys helps us connect with the larger story of the cosmos, one that stretches back billions of years and will continue for billions more. The universe may be vast and cold, but it is also full of mysteries waiting to be uncovered. And as long as there are minds to wonder and eyes to look up at the stars, the quest to understand the universe will go on. Time and space, the eternal puzzle of the cosmos. As we conclude our deep dive into the universe's wonders, we find ourselves drawn to the most fundamental questions of all. What is time? What is space? These two seemingly simple concepts are at the heart of everything we've explored, from the birth of stars to the formation of black holes, from the expansion of the universe to the possibility of the multiverse. Time and space govern the entire cosmos, yet they remain elusive, mysterious entities that continue to puzzle scientists and philosophers alike. In this final chapter, we'll reflect on the nature of time and space, examine how our understanding of them has evolved, and explore the lingering mysteries that surround these fundamental aspects of the universe. Time is something we experience every moment of our lives, yet it is one of the most mysterious and least understood aspects of reality. In our daily experience, time flows steadily forward, always moving from past to present to future. This idea of time's arrow was first formalized by the second law of thermodynamics, which states that in a closed system, entropy, the measure of disorder, always increases over time. This gives time its seemingly irreversible direction, but time, according to the theory of general relativity, is much more flexible than our everyday experience suggests. Einstein's work showed that time is not an absolute universal constant, but is instead relative, depending on the observer's motion and the strength of gravitational fields. This means that time can stretch and contract depending on where you are in the universe and how fast you're moving. One of the key predictions of Einstein's theory of relativity is time dilation. When an object moves at a significant fraction of the speed of light, time for that object slows down relative to a stationary observer. This effect, though imperceptible in our everyday lives, has been confirmed through experiments with highly accurate atomic clocks placed on fast-moving planes and satellites. Time also slows down in strong gravitational fields. Near a massive object, such as a planet, star, or black hole, the curvature of space-time causes time to move more slowly compared to regions of weaker gravity. This effect becomes extreme near the event horizon of a black hole, where time for an outside observer appears to nearly stop altogether. Black holes, those mysterious remnants of massive stars, provide one of the most extreme environments for testing our understanding of time. As matter approaches a black hole, the warping of space-time becomes so severe that time appears to stretch out indefinitely for an outside observer. For someone falling into a black hole, however, time would seem to pass normally until they reach the event horizon, after which they would be lost to the singularity, where the known laws of physics break down. This extreme warping of time near black holes leads to one of the most perplexing puzzles in modern physics, the information paradox. According to general relativity, any information that falls into a black hole is lost forever. However, quantum mechanics suggests that information can never truly be destroyed. Resolving this paradox could require a deeper understanding of time itself, one that goes beyond our current theories. One of the most interesting philosophical questions about time is whether it truly flows in the way we experience it. Some physicists and philosophers propose the idea of a block universe, where past, present, and future all exist simultaneously, much like the pages of a book. In this view, time doesn't flow at all. Rather, all moments in time exist together, and our experience of time is simply the way we perceive moving from one moment to the next. This idea has intriguing implications. If time is part of a block universe, then every moment, past, present, and future, already exists. This would mean that the future is just as real as the present, and that time, rather than being a river that flows from the past to the future, is more like a landscape through which we travel. Some physicists argue that this view is consistent with the equations of general relativity, which describe time as a dimension, much like the three dimensions of space. One of the deepest mysteries in cosmology is the question of whether time had a beginning and whether it will ever come to an end. According to the standard model of cosmology, time began with the Big Bang, the moment when the universe first came into existence about 13.8 billion years ago. Before the Big Bang, there was no time, no space, and no matter, only a singularity where the known laws of physics break down. This raises profound questions. What caused the Big Bang? Could there have been something before time began? Some theories, such as the cyclic model or the Big Bounce, propose that the universe goes through endless cycles of expansion and contraction, with time restarting with each new Big Bang. Just as time might have had a beginning, it could also have an end. If the universe reaches a state of maximum entropy in the far future, whether through heat death or some other mechanism, then time, as we experience it, may cease to have any meaningful progression. In a universe where no energy can flow and no events can occur, the concept of time itself could become irrelevant. While time presents one set of mysteries, space presents another. Space is the arena in which all physical processes occur, Yet it, too, has properties that defy our intuitive understanding. Einstein showed that space is not a passive, empty backdrop, but a dynamic entity that can stretch, bend, and warp in response to the presence of matter and energy. This is the essence of general relativity. Space and time form a unified, four-dimensional fabric known as space-time. One of the most surprising discoveries of the 20th century was that space itself is expanding. This was first observed by Edwin Hubble in the 1920s, who found that distant galaxies are moving away from us, with their light stretched into longer wavelengths. This discovery led to the theory of the expanding universe and the idea that space is not static, but constantly growing. The expansion of space is driven by dark energy, a mysterious force that makes up about 70% of the universe's total energy. As space expands, galaxies are carried along with it, growing ever more distant from one another. Over time, this expansion will result in a universe where galaxies are so far apart that they can no longer interact with each other, leading to the isolation of galactic systems. Space can also be warped by the presence of massive objects. This warping is what we experience as gravity. A massive object like the Sun bends the fabric of space around it, causing planets to orbit in curved paths. Human beings, despite our smallness in the cosmic scale, are part of this grand story. Our ability to observe, to think, to question, and to seek answers connects us to the deepest truths of the cosmos. The universe, with its endless wonders, from the birth of stars to the mysteries of black holes, from the expansion of space to the flow of time, offers a glimpse into the profound complexity of existence. And while we may never fully unravel all its secrets, our journey of discovery is, in itself, a testament to the power of curiosity and the desire to understand the nature of reality. In this universe, where stars live and die, where black holes grow and fade, and where time stretches toward infinity, we find meaning not just in the answers we uncover, but in the questions we continue to ask. The stars may fade, but the quest for knowledge endures, lighting our way through the infinite mysteries of space and time.